Hello and welcome as we dive in further to quantum mechanics. With this lecture, we will talk about some experimentation throughout the development of quantum mechanics, and specifically we will start off with the photoelectric effect. We'll see some calculations today, so a calculator will always be helpful when we dive into these types of calculations on the video. When we think about the photoelectric effect, what Einstein and Maxwell Planck were trying to develop here was looking at how the particle nature of light. Now, yes, we were thinking about the electron, but what they were trying to do is bridge the gap between the wave-particle duality. And so focusing on the particle nature of light, they were trying to express the idea that light energy must come in packets. The photoelectric effect is a famous experiment that Einstein observed that when light shines on a metal surface, electrons are produced from that surface. So he would take in an evacuated chamber, a metal surface. And what happened was as he shined light on that metal surface, and I like how it's kind of brought up here, expanded for you, the light impacts the atoms of that metal surface and then ejects an electron. So you would notice a little spark. What was developed from this are a couple of new statements. Classical theory, this was before further development, but the photoelectric effect, according to classical wave theory, attributed the electrons being emitted from the metal surface to the light energy being transferred to the electrons. In classic theory, if the wavelength of light is made shorter or the light wave's intensity is made brighter, the electrons should eject. What this means is that what was predicted was that wavelength and amplitude of a wave should affect the number of electrons ejected. That was Einstein's theory. At this time, both wavelength and amplitude were being looked at. So not only could they make the wavelength shorter and therefore more impact, more energy, they also thought the intensity, making the light brighter, would result in more electrons being ejected. The energy of a wave is directly proportional to its amplitude and frequency. That's what classical theory expected. They said if a dim light was used, there should be a lag time. Maybe the light should be like providing enough energy over time and build up that energy in the electron, and then the electron would eventually be emitted. This is wrong. What actually happened in Einstein's explanation using quantum theory was that it doesn't matter what the amplitude did not change anything at all. What does change is the actual wavelength. There was a threshold frequency or a specific wavelength that was needed in order to actually get the electron to eject. He called this the threshold frequency. Remember, we talked about the speed of light in a vacuum is how we can convert between wavelength and frequency. What Einstein decided as an explanation for what he was observing is the amplitude doesn't matter. Light being dim or being intense, being bright, doesn't have any effect on the actual energy of that light. Changing the amplitude didn't change where the electron ejected. That's what he called the threshold frequency. Right there, using a high intensity light or low intensity light, the threshold frequency was the exact same. There wasn't a lag time. It occurred right at the same amount of time. The only thing that was different was a brighter light caused the electron to have a higher kinetic energy when it was ejected. What was developed out of this was a very, very important calculation, the energy of a wave. It's calculated one of two ways. Energy is equal to h, which is Planck's constant. Planck and Einstein did all of the mathematical work to develop what the threshold frequency was, times the speed of light, c over lambda, or energy is equal to h times the frequency. Now, h is Planck's constant, 6.626 times 10 to the negative 34 joules times seconds. What that did for us is it introduced the idea that light is quantized. Light has a particle nature, and so therefore electrons have a wave-particle duality just like light. The ejection of the electrons from the metal surface by the light was proof for Einstein that there was some sort of a binding energy. An electron wants to stay with the atom, but it has a price. For the right price, that electron will leave just the right amount of energy for it to escape from the atom itself. So when it's irradiated with a shorter wavelength photon, the electron absorbs more energy than necessary. Remember, a shorter wavelength means a larger frequency, which correlates to a higher energy. So even if you decide, hey, I'm going to pummel that metal surface with higher energy than what's needed, that's great. The electron will still absorb that energy and it will be released. It's just getting more than what it needs. It will have a higher kinetic energy when it leaves. Now, what scientists would do is take a pure element, usually in a gas. It could be other forms, but usually in a gas. So it's in a tube right there, and they would put a charge through it, supply some energy, right? Energy, light, call it light energy. What that would do is it would actually, it wouldn't emit electrons, but what they noticed was that light was then emitted from the actual sample. So they didn't provide enough energy for the threshold frequency to be met, but they provided maybe a little bit less energy to see what would happen to the sample. Now, what happened to the sample is that the energy would be passed through a slit and then through a prism, and it would split into the different visible sections. And on photographic paper, right, photographic film, you could read the lines. They were visible. And these corresponded to lines in the electromagnetic spectrum of the different color scales. So when we think about atomic spectroscopy, what atomic spectroscopy is really doing is it's playing with the idea that an electron is at a specific ground state. There's a specific point, particle nature of that electron in the electron cloud. Somewhere in the atom, there's an electron just chilling and sitting there. If you supply that electron with some energy, we'll call it HV to say it's light energy, right? That electron can get excited to what we call an excited state. That electron absorbed the energy and therefore jumped to a higher energy state. Now, it didn't leave. We're not doing the photoelectric effect. It just absorbed some energy and it moved. It's kind of like in the morning, I love my coffee. In order for me to get out of bed, I have to know that there's coffee waiting for me in the kitchen. So once I get my coffee, once I get that energy, then I can actually function and I'm excited and I can move around and do all sorts of different things. But eventually, just like everyone else, I will drop back down to the ground state. When I do, I have released some energy out into the universe. right? So I can absorb energy, there's the blue, and jump up to the excited state. Eventually, though, I will emit energy and relax back down to the ground state. Now, this is atomic emission spectroscopy. We can be able to determine where electrons are in the electron cloud by studying the amount of energy released. This is a very, very powerful tool. Here are just some examples of the elemental line spectra. Like I said, every single element has a different emission spectra. White light right there in the middle, this is the whole visible section of the electromagnetic spectrum. Usually it's between 400 nanometers to 700 nanometers. You can see the different types of fingerprints. Now, hydrogen is very simple. Hydrogen has 4 lines, what we saw back up here in this lovely picture. There are the 4 lines, 1, 2, 3, 4, that very, very faint purple one. As we get more complex with the element, we see more complex emission spectra. Neon has 10 electrons. My goodness, there's all sorts of different lines there. And so what scientists were able to do is develop how to calculate the quantized state of the electron. Now, Einstein and Planck's photoelectric effect identified that light was quantized. So the emission spectra takes that one step further and says, well, electrons must be quantized then too. They must have particle nature within the electron cloud. What was developed from this was the Rydberg equation. Rydberg was a Swedish mathematician, and he helped with the development of this equation to actually analyze the atomic spectra and calculate the transition from a ground state to an excited state. Now, this work led into what we will be discussing a little bit next, which is Niels Bohr's development of the Bohr model of the atom. At this point, we do know that in the atom, there is the nucleus, which has protons and neutrons. And what was developed because of the quantization of energy was the idea that electrons exist in orbits around that nucleus. We'll call these n equals 1, n equals 2, n equals 3. And wherever an electron resides, it can shoot up to an excited state by absorbing energy, or it can relax back down and emit energy in any way, shape, or form. It can jump from any orbit based on whether it absorbs or emits energy. Now, the ground state will always be a lower energy orbital, a smaller number. Reasons for that, why is 1 the best, is because there's an attraction right here between the protons and the electrons. Opposites attract. And so when we think about the electron pulling away from the nucleus, jumping up from the n equals 1 to the n equals 3, that should require energy in our mind. That electron is trying to pull away from the center, which it's attracted to. Think about pulling a magnet off of a fridge. You have to physically go and pull it off. Now, when the electron drops back down to a lower energy orbit, that is where it releases energy, and that's the energy we see in the atomic spectra. So the Rydberg equation looks like this. 1 over lambda, the wavelength, 1 over the wavelength is equal to r, which is a constant, 1 times over 1 over n squared final, minus 1 over n squared initial. For this calculation to work, n final has to be less than n initial, and final should be a lower number, and initial needs to be a higher number. We are going to be calculating the wavelength emitted. So we are looking at the process of relaxing electrons. let's imagine that we can calculate the lambda emitted when an electron relaxes from the n equals 4 to n equals 2 orbitals. With this idea, what we want to be able to look at is plugging in. Again, n equals 4 is our initial, that's where it started. N equals 2 should be our final. If we start at 4 and end at 2, that is a relaxing process. Now R, again, will always be given to you 1.097 times 10 to the positive 7 inverse meters. Notice that we are calculating 1 over lambda. That's just how it was calculated. And so R is where we get that unit. 1.097 times 10 to the positive 7 inverse meters, 1 over meters. Let's go ahead and plug that in. 1 over lambda, 1.097 times 10 to the 7 meters to the minus 1. Just make sure that you're not forgetting those squared values. 4 minus 1 over 16. Again, 2 squared is 4. 4 squared is 16. Because of that subtraction right here, this is really why we need to make sure that our n values are going from high to low. Initial should be higher, final should be lower. All right, let's go ahead and keep chugging along here. I'll just step out a couple of the calculations so you can follow along. We'll practice a lot more of these in class. Unitless number in that bracket. We don't have anything in terms of units for the orbitals. So this is one time when the n value there is just going to be a whole number. 1 over lambda is 2.06 times 10 to the 6 meters to the minus 1. And then we'll take the reciprocal of that. 1 divided by that answer. 4.86 times 10 to the negative 7 meters, or 486 nanometers. So we would see that's in the visible section. So that's one of the lines that we would see for this transition. Now, again, you wouldn't need to come up with all of those transitions. We'll see a nice little visual in a little bit with bringing in the Bohr model. All right. Rutherford did not explain any of the structure of the electron cloud. It was Bohr that developed a model of the atom to explain how the structure of the atom changes when it undergoes these energy transitions that were observed in the atomic emission spectra. Bohr's major idea was that the energy of the atom was quantized, and the amount of energy in the atom was related to the electron's position in the atom. And so the idea of orbits was starting to be developed, but not the idea of the energy of each orbit. And so that's what Bohr really brought to the table, was this idea that he was able to explain the atomic spectra and explain where the fixed orbitals were around the nucleus. It kind of looks like the nucleus is the sun and all of the electrons are planets rotating around it. And the transitions, either energy being absorbed or energy being emitted, were those lines in the emission spectra because of these fixed states. So electrons travel in orbits and they're fixed distance from the nucleus. Those are what he called stationary states. And so therefore the energy of the electron was proportional to the distance of the orbit. When we think about being close to the nucleus, again, we kind of already mention this, electrons attract protons. So the closer the electrons are to the nucleus, the more stable they are. They are happy to be there because they feel that attraction. As we emit or as we see the electrons absorb energy, they can jump up to higher orbitals. It's when electrons emit radiation, they should be jumping down from high energy to low energy. That emission spectra should be making the electron relax back down to a lower energy state. The distance between the orbitals was determined by the energy of the photon. So Bohr took this a little bit further and actually was able to say, what is the energy difference? Not only taking the wavelength emitted, he then went back and calculated the energy using the calculation that we had in the photoelectric effect, right? So we can see a couple of different cases here. All valid transitions and understanding the emission spectra that was visualized for different elements. Now, there's our little nucleus right there with the protons, that red dot. N equals 1 is the closest orbital to the actual nucleus. N equals 2 is a little further away. N equals 3, N equals 4, and it can go up as far as we can imagine. As we start to dive into chapter 3 and looking at the periodic table and elements and where these fit into specific elements, it will really start to be eye-opening of the expansive nature of quantum mechanics. Lovely. Another player in this time was Louis de Broglie. And de Broglie was around in 1924. He really wanted to emphasize the wave nature of matter. The particle nature was very well understood at this point with the Bohr model of the atom. And the transitions were understood as particle nature, even though they had some sort of wave nature with that emission. The actual movement of the electron between orbits was very, very much focused on the particulate side of the electron. And so Louis de Broglie really came in order to say, hey, what about the wave nature? We're missing that part of quantum mechanics. And so he looked at electron diffraction, which electrons diffract just like waves do. And so they must travel in that wave style up and down motion, right? Even though we're not talking about light, we're now talking about the electron. If light can behave like a particulate, then why can't electrons behave like a wave? And so duality, just like the cat, right? Just like the thought experiment from Schrodinger, de Broglie came up with his wavelength. And the de Broglie wavelength, usually abbreviated lambda with a dB, is related to the kinetic energy of the actual particle. Specifically, we're going to talk about the electron. Now, this de Broglie wavelength, this wave nature of matter, is the wave nature of all matter. It doesn't matter how big or small. Everything that has matter has wave-particle duality. Now, we will be able to discuss why we don't see a car moving in this same pattern of up and down, and why we see an electron react that way or move that way. But again, everything that has kinetic energy has that motion of wave particle duality. And so this is his wavelength equation. H, Planck's constant, divided by mass times velocity. So let's just define a couple of things. This is Planck's constant that we had seen before, again, always given to you. 6.626 times 10 to the negative 34 joules times seconds. This is mass. Now for mass, we have to be in kilograms here. The reason is because of the joule. 1 joule is defined as 1 kilogram meters squared over seconds squared. And so mass, in order to be able to calculate correctly and cancel out with the joule, we have to have mass in kilograms. V is velocity, the movement in meters per second. So when we look at this calculation, we can calculate the wave nature of any moving particle, whether it's a subatomic particle or a macroscopic particle.